Hello everybody, this is again Dr. Sergey Sarkisov, and I'm going to show you how to prove a very cool arithmetic identity via induction. So let's go. The one formula that I want to look into is, first of all, remember we know the sum of the first k integers, right? So if I put this means what? This means it's a arithmetic series, right? It's actually the summation of a sequence of 1 and 2 and 3 and 4 and all the way to k, the first k natural numbers. So we're adding them up, and there's a formula for this, right? In fact, we derived it last time. What is that formula? And if you remember, and we can show this also and prove it by induction, which we will do in a moment actually, but the formula is k times k plus 1 all over 2, right? And so this formula, let's first prove this one, okay? And let's do this as follows. Let's what we do is let's check for the case n equals 1, okay? So if what is it? If n equals to 1, then let's call this actually the sum sk, okay? And so that's the kth sum being the first sum of the first k natural numbers. So now n equals 1. What is my s1? Well, we know it's just 1 and that's it. The first natural number, we don't add it to anything because it's just one number. And what is it equal to 1 times 1 plus 1 over 2? It definitely does, right? 2 over 2 is a 1, check mark. Okay, so that formula worked. Let's try n equals to 2, which we don't necessarily have to, but let me just show you. S2 is equal to what? 1 plus 2 is equal to 3. And is it equal to 2 times 2 plus 1, right? K times k plus 1 all over 2. Well, the 2's cancel, and yes, it is indeed a 3, check mark. N equals 3, similarly, S3 will equal to 1 plus 2 plus 3 is equal to 6. And is that true by the formula? Well, let's see. Is it equal to 3 times the 3 plus 1, which is 4, which gives us 12 all over 2, which indeed is the 6. Okay, so the question is now, what do we do to prove for all numbers n? 1, 2, 3, and so on, right? The induction, basically what we do is we assume this works, this holds for n equals k, and we prove that the formula holds. If that holds for n equals k, then we can prove that it holds for n equals k, what is it, 4 n equals k plus 1, then we're done, because basically 1 and then 1 means 2, and then 1 and 2 and then means 3, and so all the natural numbers going on to infinity, 1, 2, 3, 4, 5, and so on, it will work for all of those, right? And so we're proving this formula by induction. And so let's do this. We're going to use the result. Again, what does it mean, assume this? It means that we just had what we had written, that k is exactly k times k plus 1 all over 2. That's what we're assuming. And we want to show that basically if we put k plus 1 times k plus 1 all over 2, that should be that's if we do that, right? So let me show you the k plus 1 sum. So what is sk plus 1? Let's find the formula for this sum, and let's see if it makes sense. That it is indeed, again, we're trying to show this. Right? That's what we're trying to show ultimately. I'll erase this in a moment. If we can do that, we're good, right? Because this is exactly what we're trying to show, that we're using now for substituting for the formula k plus 1, and it still works. So let's check it out, right? You see it? No, you don't. So what it really means is the sum of the integers 1, 2, 3, all the way to k, right? And then also that last one, k plus 1 now. Well, the first k, right, is actually sk, and then plus that k plus 1 at the very end. Well, that's equal to, by the assumption, by the inductive assumption, we have that this is k times k plus 1, this right here, this sk, right, all over 2. That's what we're assuming, that the formula works for k, sk, and then of course plus a k plus a 1, right? And that's equal to k squared plus a k all over 2, and make a common denominator, so plus what? 2k plus 2 all over 2, right? Make this 2 over 2 times top and bottom. And so now we have equals, let's just equals, what is that? All over 2 we have k squared plus 3k plus a 2, right? See that, all that added up, and then all over 2. And that's what, equal to k plus 1 times, if you factor it, k plus 2, right? And that gives you that k right there, and 2k, you get 3, 3k in the middle there for the outer and inner terms when you do the FOIL method, okay? Expanding. And so now when we factored it, I just checked it, that this is correct. And all over 2, and you see we're almost done because this is actually what? K plus 1, great, times k plus 1 plus 1, that's what k plus 2 is, all over 2. And we are done. That's the proof. Now, I want to show you a cooler formula, something more interesting. So this is this is not the one I was actually going to do. Let me show you something a little bit more interesting. Let me show you this one. Let's look at the sum of the first cubes, first natural numbers cubed, though, the cubes of those. So imagine I called this sum like this, sk, equal to the summation, similarly, I equals 1 to k, but now I'm going to do I cubed. In other words, I'm doing 1 cubed plus 2 cubed plus 3 cubed all the way to k cubed, okay? The cube, sum of the cubes. That's interesting, right? What happens? Let's try some numbers. I don't really want to guess a formula, but I want to see something really cool that happens. So, and then maybe notice something here. So look, if we do, because we don't even know what we're trying to show, right? Let's just play around with this for a little bit. So let's do this. Let's get a kind of a color like this. All right, try S1. What does that equal to? That's 1 cubed is 1. S2, right? What is that? 1 cubed plus 2 cubed, that's 1 plus 8, and that's a 9. Okay. S3, what is S3? It's 1 cubed plus 2 cubed plus 3 cubed. That's the 9 that we had plus a 27, right? And that's equal to 36. Notice some patterns in these numbers. I'm noticing 1, 9, 36. Interesting, okay? Let's do S4 and S5. S4 is equal to the sum of the first 4 cubes, right? And that's going to be, we now have 36 plus that 4 cubed. What is that? 36 plus a 64, right? 4 cubed, and that's equal to 100. What is S5 going to equal to? Well, if you do S cubed, 1 cubed, 2 cubed, 3 cubed, 4 cubed, that summation now we know is 100 plus a 125 from 5 cubed, and that's equal to 225. Okay, great. Because another thing I'm noticing is that these are all perfect squares. And we can go on and on. So we can not only show that SK is going to be a perfect square, right? But it's something special about a perfect square. Watch this. S1 is equal to 1 squared, right? 1 is 1 squared. S2 is equal to 3 squared. See the 9? It's 3 squared. The S3, 36, what is that? That's exactly 6 squared. And what is S4? S4 is 100. That's 10 squared. And S5, finally, is a 15 squared, right? 225. What's cool about this, when you even notice anything, is that these numbers, what is it? These numbers 1, 3, 6, 10, 15 are triangular numbers. In other words, remember, this is 1 is actually just 1, right? It's also S1 squared. Remember the numbers S1, S2, the older arithmetic series. Look at this. You got a 1, a 3, a 6, right? And so S2 is a 3. The 3 is an S2. So, and we're squaring it. So S2 squared. And what about this? This is 6. This is actually S3 squared. And if you check it out, if you do a 6 plus 4, you get S4 to 10, right? And you get that squared. And so now, guess what this is? This is S5 squared. Really cool, right? So my guess is hypothesis. Okay, I'm going to guess that my SK, what is it? That the cursive SK, okay, in other words, the sum of the cubes, right? I equals 1 to k I cubed is going to actually equal to the sum of the numbers from 1 to k, just the natural numbers, the sum, the arithmetic sum squared. In other words, what we're saying is sk and then squared. That's a cool formula if we could show it, right? Because we kind of actually showed it for 1, 2, 3, 4, 5 now. For k equals 1, 2, 3, 4, 5. So proof by induction. Proof by induction. And this is not going to be as bad as we think. So look, it's very similar to what we did the last proof. Proof by induction is as follows. K equals 1, 2, 3, 4, 5, or n, let's call it n, right? They all work. We already checked it up just above. We're playing around with it. So work. So we could even just do n equals 1, but I just did 1, 2, 3, 4, 5 just to be more confident. This is why we kind of we're trying to check this formula, because actually we think probably it's going to work for all of the numbers, 1, 2, 3, 4, 5, and on. So let's assume it works that for n equals k, this is true, that this is equal to this, right? This sum of cubes is equal to the sum of the natural numbers, the arithmetic sum squared. Okay, so now showing for this is our proof, is that we want to show this is working for k n equals k plus 1, right? So let's do this. Let me show you what's going to happen. Let's do s k plus 1, okay? And what is that equal to? Well, that's equal to the sum of the first, what is it, k plus 1 cubes, okay? And that's going to be 1 cubed plus a 2 cubed all the way to, plus a 3 cubed plus all the way to a, we get a k cubed, and then after that a k plus 1 cubed, right? Okay. And that's equal to, well, what is all this right here? What's the point of all this induction? What was that step right there? This right here is important because we know that this is actually my sk, right, plus a k plus 1 cubed. That's how this is working inductively, right? So now look, this sk, I'm assuming it's equal to that sk squared, right? We know a formula for sk. Remember that. We know that formula above there. Where is it? Right here. 1 second. Right there. That's a formula. K times k plus 1 over 2. So we know we've shown that formula now. But sk squared and then plus a k plus 1 cubed. Okay. Okay. Well, let's see what happens here. Let's plug in our formula. Let's just do that really quickly here as follows. Our formula, let me just do it one time like this, is k times k plus 1 all over 2, right? And I'm going to square it. That's the goal, because sk, we're going to get this, so we're going to do the formula there. I'm going to square it, and plus a k plus 1 cubed, right, equals to what? I'm seeing it's, let's actually factor out a k plus 1 squared. That'd be easier maybe that way, right? It's everywhere. K plus 1 squared times, if you check it out there, it's going to be k squared over 4, right, left, and this is plus a k plus 1. Okay, that's what's left there. Now, this is equal to k plus 1 squared times, let's see what that is, all over 4, right? Let's put it over 4. And then this is going to be k squared plus a 4k plus 4. And we know what that is, right? That's a square of k plus 2, actually, if you remember how to factor this. So it's k plus 1 squared. That's a k plus 2 squared there, all over 4. Okay. Interesting, right? Actually, let me be kind of clear with what we, like if you're looking at the notes, that this is really what happened, is that we had the 4 under this, right? That would make more sense. So, okay, now we have this, and what is that equal to? That's equal to k plus 1 times k plus 1 plus 1, right? And then we're squaring all of this all over 2. 4 is a 2 squared, and everything squared there, guess what that is? That's actually s, just a printed capital S, k plus 1, right, squared. And we have shown that this is equal to this. It works for k plus 1 just as it works for k, or any number less. So, we are done. Thank you everybody for looking over this. And again, just wanted to show you that this is a cool formula that we have derived. And let me put it in a little box here. 1 second. It's a really cool formula, I believe. So there we are. Okay. All right. See you next time.